our next specific reaction is fluorination, the substitution of a hydrogen with a fluorine. Fluorine substitutions for hydrogen are very, very important in medicinal chemistry, in bioactive, particularly pharmaceutically active medicines. Why is that? Well, typically what happens in medicines is that when it passes through your body, eventually it gets to the liver. And in the liver, the medicine gets oxidized by cytochrome P450, and it does that by inserting into a carbon-hydrogen bond, putting an oxygen into it, and making a hydroxyl functionality. That hydroxyl functionality can continue to be oxidized, or maybe it's passed out through the kidneys or some other mechanism. And so one of the key ways that we improve medicines, that is, we can improve what's called the pharmacokinetics of that medicine, making it last longer in the body and thus requiring a lower dosage to achieve the desired clinical effects. And lower dosage is better, right? Lower dosage typically means fewer side effects. We can identify those carbon-hydrogen bonds that get oxidized, and we can replace hydrogen with fluorine. Now, why does that work? Because fluorine is not so easily oxidized. That is, the carbon-fluorine bond is not so easily oxidized. And so the compound is much more difficult for cytochrome P450 to oxidize. So fluorination is a very, very important part of medicinal chemistry, and can take what is not so great clinical candidate for a medicine and turn it into something that might actually be useful in the clinic. So how do we obtain fluorinated products? Well, fluorine is actually one of the most difficult things to incorporate into a molecule. And so we'll learn a few methods. In fact, it's still one of the leading edges of research, for instance, just putting CF3 groups on in a highly efficient manner. So let's go back now to electrophilic aromatic substitution. How do we accomplish electrophilic aromatic substitution? We need an F plus reagent, right? We needed an electrophile, so we need something that's the equivalent of F plus. But what's the most electronegative element in the periodic table? Well, of course, it's fluorine, right? So how do you get something where you can generate effectively an F plus? And there's a reagent. This fluoroamine, which is an ammonium cation, it's in fact a dication, so this is a very high energy species, is capable of delivering a fluorine cation equivalent. FTEDA, that's for triethylene diamine. Ethylene, there's ethylene, CH2CH2, three of them, 1, 2, 3, triethylene diamine. Nitrogen and nitrogen is actually a diammonium, triethylene diammonium, tetrafluoroborate. Okay, so the abbreviation FTEDA BF4. Now, as I've already pointed out, we'll have predict the products, and we can use this abbreviation, FTEDA-BF4, and many other abbreviations. But for chemistry, and this is different than biology or other disciplines, just using the abbreviation is not sufficient. The abbreviation must bring to mind a chemical structure for you. Okay, and if it does that, then you're using it effectively. If it doesn't bring to mind for you a chemical structure, then eventually you're going to get lost. Because if all of you biologists, pre-professionals, pre-med, pre-vet, pre-dent and so forth, pre-farm. In biology, you probably all know what NADHP is, right? But what's the chemical structure? Can you draw it? You see, that's one of the things we're going to be learning eventually, very late in this semester. These things need to have a chemical structural meaning, and that's one of the big differences between us chemists and biologists. I want you to know that chemical structure, because if you know that, then you can develop the intuition to use it in other places. All right, so this reagent now, all of this combined, will produce fluorinated benzene or fluorobenzene. Now, how does this occur? Well, just as we've seen already, the benzene ring acts as a nucleophile. It attacks this, and the rest of this ammonium molecule acts as the leaving group. This produces our now familiar electrophilic addition intermediate that has lost aromaticity. The counterion to this will be one of those BF4s, and of course those fluorines have lots of lone pairs. That could be our Lewis base. And we regenerate the aromatic nucleus. And again, it's that aromatic stabilization energy that causes us to have substitution instead of addition.